So today we are going to start our second last unit, that is sixth unit, and it is on lattice vibrations. So far we have studied about the band theory of solids, in which we discussed that an electron moves under the influence of a periodic potential generated by the positive ion cores, which are located with respect to each other at regular interval or at a certain interval. So with this band theory of solids, we considered basically two things. One, the nearly free electron model, in which it was considered that the moving electron interacts with the positive ion cores weakly, or the potential introduced by the positive ion core is not so strong that it captures the electron at a particular atomic site. Rather, it is weak. And when the electron moves under the influence of weak or strong periodic potential, its wave function gets modified and the electron becomes the block electron. And if you have gone through the video shared by me, you would see that the behavior of a block electron is completely different. The behavior of a block electron is completely different from that of a free electron. The block wave function has a plane wave which gets modified by a modulating function which has the periodicity of the lattice. So this nearly free electron model, in which the periodic potential is weak, it introduces the gap in energy or the discontinuity in the energy at the zone boundaries. And we considered the reduced zone scheme, the extended zone scheme, and the periodic zone scheme. With the help of this band theory of solids, we could explain why some materials should be conducting, others should be insulating, and we may have some materials which are in between conductors and insulators, and these materials are known as semiconductors. I have not changed any slide, I am just talking orally, so don't worry about that. And with the help of this band theory, we could also explain why certain metals like aluminium, antimony, bismuth should have the positive value of Hall coefficient, because in the band theory, when we consider the Fermi surface is not spherical in nature as proposed by Sommerfeld free electron theory, but it has different shapes, and depending upon the number of electrons, we may have the different shapes or very complex shapes of Fermi surface. We have seen it for the monovalent atoms having the BCC structure, monovalent atoms having the FCC structure. We have also seen it for the divalent atoms, and the trivalent and tetravalent or pentavalent atoms materials will have very complex shapes of Fermi surface. And these complex shapes of Fermi surface, which lie in different different Brillouin zone, give rise to the complex shape of Fermi surface. So we may have the particle-like behavior, means electron-like behavior, or we may have Hall-like behavior. So depending upon whether we have the dominance of electron-like behavior or the Hall-like behavior, we will have accordingly the Hall coefficient for that particular metal. So with this theory, we could explain why certain materials could have the positive value of Hall coefficient. I hope it is clear to you. But again, it is also not a complete theory. It is also not a complete theory in many sense. For example, if you consider the case of sodium, sodium atom has one electron in the outermost shell. Therefore, according to band theory, the 3s band formed by having n number of atoms means 6.023 into 10 to the power 23 atoms per mole or per centimeter cube, then the 3s level, energy level of individual sodium atom would be converted into a band. But 3s level is having only one electron, therefore 3s band in a sodium metal or sodium solid would be half filled. Do you agree on this? Do you understand what I am saying? क्या आप इस बात को समझते हैं, एग्री करते हैं? Yes or no? मैं बोल रहा हूं कि जो 3s सोडियम का एनर्जी लेवल होता है एक सिंगल एटम का, उसमें एक इलेक्ट्रॉन होता है, और जब हम बहुत सारे सोडियम एटम से सोडियम मेटल बनाएंगे तो 3s बैंड में कन्वर्ट हो जाएगा, लेकिन दिस बैंड वुड बी हाफ फिल्ड बिकॉज वी हैव ओनली वन इलेक्ट्रॉन. यदि 2 इलेक्ट्रॉन होते, एस सेल में 2 इलेक्ट्रॉन आ सकते हैं तो पूरा बैंड भरा हुआ होता, लेकिन यहाँ पे हाफ फिल बैंड होगा. सो अकॉर्डिंग टू बैंड थ्योरी, sodium should always be a metal. Do you agree or not? सोडियम मेटल होता है, लेकिन if we try to increase the interatomic distance between the sodium atoms or sodium ions in a solid, if we try to increase it, the conductivity of sodium will decrease, and there would be a particular interatomic distance known as the critical interatomic distance, beyond which, if we increase the interatomic distance, sodium metal would convert into an insulator. But according to band theory, because the band still is half filled, sodium should remain a metal. But experimentally, it is seen that if we expand sodium after a critical interatomic distance, sodium would convert into insulator. Such type of metal to insulator transition is known as Mott transition. It is given the name Mott transition after very famous scientist Sir Neville Mott, who got Nobel Prize somewhere in 1997 or 1978 in physics. So this is a brief idea of the failure of band theory of solids. And there are other type of oxides, for example, nickel oxide, NiO. If we consider the nickel oxide band structure, we see that the band is partially filled. So according to band theory, nickel oxide should be a metal, but it is seen that it is actually an insulator. So in oxides also this band theory fails, and other example I gave you of sodium where this band theory fails. The second thing is that in the band theory we ignored the electron interaction. Still we are saying that electron which is moving in the metal or solid remains unaffected by the presence of other electrons. But there is definitely an electron interaction, and when it is considered, we get peculiar behavior of solids, and such systems where we consider the electron interaction as well. These are known as correlated electron systems, in which the kinetic energy of the moving electron becomes smaller than the Coulombic repulsion between the electrons, or in other words, the Coulombic repulsion between the electrons dominate their kinetic energy. So such systems where we consider the electron interaction are known as the correlated electron systems, and we also have strongly correlated electron systems, and these are the topics of recent research in last 20 or 30 years. So these are all research topics: mode, metal to insulator transition, strongly correlated electron systems, and they give rise to very interesting physics. So this was just a brief idea to give you about the failure of the band theory of solids and what is going on in research field when we consider the electron interaction. All right. So another problem with the band theory of solids is that we consider the ions or atoms which have the periodic arrangement among themselves. They remain fixed at their respective sites. They do not move or vibrate. But if you consider our solid at room temperature or at any other temperature, because of the finite temperature, atoms or ions will be vibrating around their equilibrium positions. Therefore, we need to consider these lattice vibrations, and we need to understand these lattice vibrations. So this is the topic of today's and for the coming classes discussion. We have seen that the atoms or ions inside a solid are bonded with each other, and while we discuss the lattice vibrations, we consider that these bonds are replaced by springs. So when we consider the lattice vibrations, we say that ions are attached with each other through springs or by springs. So these atoms are vibrating, springs are getting compressed or stretched. Is the background of today's lecture clear to you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So, okay. So now we proceed further. So far, while discussing the band theory of solids, we have assumed that the atoms in a lattice are stationary at the respective positions. However, according to the kinetic molecular theory, the atoms in a solid are constantly vibrating about their equilibrium positions by stretching and compressing their springs. And we have considered the ions or atoms are attached with each other by springs. So in order to understand the lattice vibrations, first we consider a chain of identical atoms of mass m, where the distance between two neighboring atoms or ion is denoted by A. This is equilibrium distance. Equilibrium distance means when the atoms are not vibrating. So this is the interatomic distance denoted by A. And we have chain of identical atoms Identical atom means every atom will have equal mass, that is denoted by m. So we can define the position of any atom. For example, if we define the position of nth atom, we denote it by x, and in the subscript we have the number designated to atom. So xn is any instantaneous position of the nth atom while it is vibrating around its equilibrium position, and its equilibrium position is denoted by x n equilibrium is equal to Na. It is nth atom and it is at a distance of n times a from the first atom from the left side. Okay, and this xn is any instantaneous position of the nth atom around its equilibrium position. So if we take the two things, we can calculate what is the displacement of nth atom at any instant when its position is xn. So what is the net displacement of nth atom around its equilibrium position? It would be given by delta xn is equal to xn minus xn equilibrium, and xn equilibrium is equal to Na. So this is kind of arrangement we have shown here. We have one-dimensional chain of atom in which the atoms are held together with the help of springs, and the interatomic distance is a. So we consider any atom, nth atom, and we will consider that it will interact only with its nearest neighbor. So if we consider nth atom, it is going to interact with n plus 1th atom, and it is going to interact with n minus 1th atom. So for example, if we consider the 5th atom, it will interact with the 6th atom and it will interact with the 4th atom. This is just for making the thing simpler. If we consider the interaction of any atom with nearest neighbor or next to next nearest neighbor also, the result would remain more or less same. So for this one-dimensional chain of atom, we can plot the potential energy that is given by V, and this potential energy, you have seen that it varies like this when we bring two atoms together and we form a bond. So this x equilibrium is known as the bond length, and it is the equilibrium distance. So beyond that, on the right side, we have the attractive force, and here we have the repulsive force. So accordingly, we have the attractive potential energy to the right of equilibrium position, and to its left we have the repulsive potential energy. So this is the curve shown by the blue line. It is the actual graph that we get. But hello, somebody is saying something? Okay, there is also a red curve. This red curve represents the harmonic approximation. Under harmonic approximation, we consider that the displacement of the atom from its equilibrium position is not large. Therefore, the potential energy varies quadratically, or potential energy varies as the square of the displacement. So this red curve here represents the potential energy under harmonic approximation. And you can see on the blue curve, we have x minimum and x maximum. So this is the distance, x maximum is where the atoms goes on the right side, the maximum distance, and it is the minimum distance on the x minimum represents the minimum distance on the left side. And actually it is not, x minimum is not equal to x maximum, because when we heat any solid, it expands. Therefore we can see that x maximum minus x equilibrium is greater than x minimum minus x equilibrium. This is, we can verify when we heat any solid, it expands, it does not contract. Therefore x maximum minus x equilibrium must be greater than x minimum minus x equilibrium. Or we can say that the average value or average displacement of any atom is much greater than x equilibrium. All right. So if it is so, then what we can do, we can do the Taylor expansion. We can do the Taylor expansion of the potential energy around the equilibrium position, and we will get several terms. We consider only few terms. So x equilibrium, this is the equilibrium position, plus k bar divided by factorial 2 x minus x equilibrium square. So k bar here represents the spring constant. K bar here represents the spring constant. I have put bar here to differentiate k from the wave vector. K bar represents here the spring constant. In some books it is represented by beta, in some books it is represented by alpha, in other books it is represented by different symbol, but here I am considering the spring constant to be denoted by k bar. So the third term would be minus k bar by factorial 3 x minus x equilibrium whole cube. Now if we consider the harmonic approximation, in which there are only small deviations from the equilibrium, the higher terms are much smaller than the second term. Therefore under such harmonic approximations, the potential energy varies quadratically, and this is what is shown here by the red line. So we consider any two neighboring atoms denoted by I plus 1 and I. We consider ith atom and we consider I plus 1th atom. So their potential energy, the potential energy of the whole system would be given by summation I v x iota plus 1 minus xi. And if we consider only the second term, the potential energy in terms of the spring constant would be given by 1 by 2 summation I k bar x iota plus 1 minus xi minus a to the whole square. And it can be written as summation over I k bar by 2 delta x I plus 1 minus delta xi to the whole square. So this is the potential energy that varies quadratically. And if we calculate the force of any arbitrary nth atom, we can calculate it by F is equal to minus the derivative of total potential energy with respect to the position of nth atom, and it would give us k bar delta xn plus 1 minus delta xn plus k bar delta xn minus 1 minus delta xn. So this is the force we are going to we are going to get. And if we have force, this will be a compressive or the stretchive force. Due to this, the atoms will start vibrating, and they will execute under the harmonic approximation. They will execute the simple harmonic motion. And we have studied, if we consider one-dimensional harmonic oscillations, we can solve them using the quantum mechanics, using the Schrodinger equation, which is given by d2 psi over dx square plus 2m upon h cross square E minus Vx psi is equal to 0. And from the quantum mechanics, we know the energy values for one-dimensional harmonic oscillator is given by n plus half h cross omega. सभी लोग जानते हैं इसको, E n is equal to n plus half h cross omega.
Yes, sir.
The energy of one-dimensional harmonic oscillator.
Yes, sir.
So omega is angular frequency given as under root k bar upon m, and we will not say angular frequency in the following discussion. We will just use the term frequency, but frequency, whenever we say frequency, it means angular frequency. The energy levels are equally spaced with 0-point energy given when we substitute n is equal to 0, we have E naught is equal to half h cross omega. So this is the energy that harmonic oscillator possesses even at t is equal to 0 Kelvin. The energy separation between the consecutive energy levels is h cross omega, which represents the amount of energy absorbed or emitted by the oscillator when it is excited or de-excited to a neighboring energy level. This quantum of energy that is absorbed or emitted is known as phonon. And phonon is the same thing or analogous to, like we have photon for electromagnetic radiation. Similarly, phonon, we have the quantum of lattice vibrations. So by quantum of lattice vibrations means the lattice can absorb or emit energy in the form of phonons, n h cross omega. So the energy of lattice vibration is also quantized, and the lattice can absorb or emit energy only in terms of n h cross omega. It can absorb energy h cross omega to h cross omega. Similarly, it can emit energy h cross omega to h cross omega, like this. So the quantum of lattice vibrations are known as phonon, in analogy with the quantum of electromagnetic radiation, which is known as photon. Similarly, when we have the when we consider the magnetism, and we have ferromagnetism or antiferromagnetic material, in which we have all the spins in a ferromagnetic material, we have all the spins aligned in one particular direction at t is equal to 0 Kelvin. If we excite one spin, it means if we flip one spin, then a wave is generated in that ferromagnetic material, and that wave is known as spin wave. And the quantum of that spin wave, in analogy with electromagnetic and lattice vibrations, is known as magnon. So the quantum of magnetic excitations is known as magnon. The quantum of electromagnetic radiation is known as photon. The quantum of lattice vibrations is known as the phonon. When a lattice vibration interacts with another lattice vibrations, or it interacts with electron, or it interacts with a photon in the crystal, it does so if it were having a momentum P phonon is equal to h cross k, and energy of the phonon is given as h cross omega. So lattice vibration can interact with another lattice vibration. It can also interact with electrons. So we have electron phonon interaction, and that is how we explain superconductivity through this electron phonon interaction. So a phonon or lattice vibration may interact with another lattice vibration. It may interact with another electron, or it may interact with a photon. So it does so if it were endowed with a momentum and energy. So if the phonon momentum is given as h cross k and its energy is given as h cross omega. Since the atoms in a solid are coupled to each other by bonds or springs, atomic vibrations are also coupled. If one atom is vibrating around its equilibrium position, so this means that uh, the all atoms are vibrating around their equilibrium positions, because these atoms or ions are attached with each other. These coupled vibrations lead to waves that involve cooperative vibrations of many atoms, and they cannot be represented by independent vibration of individual atoms. Things would be clear to you when we proceed if something is not clear. As an atom vibrates, it transfers its energy and momentum to the neighboring atoms, and the coupled vibrations produce traveling waves in the crystal. Such collective vibrations of atom in a lattice are known as lattice vibrations. So lattice vibrations or vibrations in a wave can be of two types: the longitudinal vibrations or the transverse vibrations. So here we saw a chain of one-dimensional chain of atoms attached with each other through springs. The equilibrium interatomic distance is A, and this is how at any instant we capture the vibration. So this second atom is displaced from its equilibrium position by amount x. So now the distance between the two atoms is A plus x. So these are longitudinal vibrations in which the atoms vibrate along the propagation of wave, or along the direction of propagation of wave. So these are known as longitudinal vibrations, and the transverse vibrations are in the perpendicular direction of the motion or the direction of propagation of wave. And we can have two perpendicular directions. Therefore, for example, if the wave is traveling in x direction, so we can have vibration along the y direction, or we can have vibration along the z direction. So therefore, there are two components of transverse vibrations of lattice. So far so good. And but a solid is composed of discrete atoms. Atoms are not, the solid is not continuum as it looks, but it is made of discrete atom. Every atom is separate from another atom. So therefore, solid at the atomic level, if we analyze the solid at the atomic level, it is made of discrete atoms. The solid is not a continuous solid, but it is made of discrete atoms, and this discreteness must be taken into account in the discussion of lattice vibrations. However, when the wavelength of lattice vibrations are very long in comparison to what? Very long in comparison to the interatomic distance. The atoms are vibrating and they are producing a lattice wave. So if the wavelength of this lattice wave is very large in comparison, very large in comparison to the interatomic distance, and when the wavelength is large, the wave vector would be smaller because the two are related. K is equal to 2 pi upon lambda. So if lambda is large, K would be smaller. So we are saying that whenever the wavelength of lattice vibration is very long, or in other words, the wave vector is small, we may discard the atomic nature and treat the solid as a continuum or a continuous medium. Such vibrations are referred as elastic waves. Such vibrations are referred as elastic waves. So sound waves in solid, for example, if we have that ultraviolet waves which propagate inside the solid, these are also known as the elastic waves, and for those waves the solid behaves as a continuum. But we will also see the cases when we need to consider the discreteness of atoms. So the relation between the frequency and the wave number k of an elastic wave or a sound wave is known as dispersion relation. So this is the dispersion relation for sound wave, where omega is linearly proportional to the wave vector, and the proportionality constant is the speed of sound. So Vs is the velocity of sound wave in the solid, and Vs is proportional to under root y divided by rho, where y is the Young modulus or the stiffness coefficient, and rho is the mass density. And Vs is of the order of 10 to the power 5 centimeter per second or 10 to the power 3 centimeter per second. Optical wave or the electromagnetic wave traveling in vacuum has a dispersion relation which is of this form. We have a linear relation between omega and k. But we would like to see, when we consider the lattice vibrations, waves are propagating inside the solid, we would see how this dispersion relation between omega and k will get modified. So as the wavelength decreases, k increases. The discreteness of the atoms becomes more and more significant because the atoms begin to scatter the wave. The effect of scattering is to impede the propagation of wave by decreasing the velocity of wave. Recently, we have discussed the Bragg reflection from the lattice plane, and in the reciprocal lattice, we said that if any wave having wave vector that starts from the origin and terminates at the zone boundary, that wave is Bragg reflected at the zone boundary. So similarly, when the wavelength decreases, means k increases, and when k is the k of the lattice wave is of the order of half of the first Brillouin length, such wave will be scattered from the will be reflected back from the atoms, and this wave, the resultant of two waves, one is traveling in the positive x direction and it gets scattered from the atoms. It travels in the minus x direction. The resultant of the two waves will give rise to a standing wave, and hence the group velocity for such a wave whose wave vector is equal to half the length of first Brillouin zone would be a standing wave, and we would see the dispersion. So as the wavelength decreases or k increases, means scattering increases, lambda decreases, or the velocity of lattice wave decreases, and exactly at the zone boundary, a lattice wave would be a standing wave with group velocity equal to 0. So the dispersion relation under that case, you see the k is increasing. As k increases, there is a deviation. There is a uh, deviation of omega from the from the relation when we consider the solid to be a continuum. So the dashed line here is a graph that represents that considers the solid to behave as a continuum. But when we consider the discreteness of atoms, which comes into picture at higher k values, the omega starts decreasing as a function of wave vector. So in order to understand this behavior, in order to understand the deviation of the elastic waves from the linear omega versus k relation, we need to consider one-dimensional chain. So first we consider one-dimensional monoatomic crystal. So one-dimensional monoatomic crystal means in every unit cell we have one atom. We have one atom in every unit cell. Atoms begin to vibrate. So this is one-dimensional chain of atom in which this is nth atom. So and other atoms are represented by n plus 1, n plus 2. To its left we have n minus 1th atom, n minus 2th atom, like this, and these atoms start vibrating. So at any instant, the displacement of nth atom from its equilibrium position is given by delta xn. Accordingly, the displacement of n minus 1th atom from its equilibrium position is delta xn minus 1, and like this. For this, we need to see how much force is exerted on the nth atom by the vibrations of n plus 1th atom and by the vibration of n minus 1th atom. So the force would be given by Fn is equal to the spring constant k bar multiplied by delta x n plus 1 plus delta x n minus 1 minus 2 delta xn, and this force is nothing but mass into acceleration, which can be written as m into d2 delta xn divided by d2 square. So it can be written as second derivative of delta xn. So this is the equation we have. Now we say this ansatz. Ansatz mean we make an educated guess that what could be the solution of this differential equation, and we say the solution is like this. It represents a traveling wave of the form delta xn is equal to a is amplitude e to the power iota omega t minus I k xn, and xn we know it is equal to na. So the solution is delta xn is equal to a e to the power iota omega t minus I k x n a. Atoms oscillate with the same frequency. That's why we have only one frequency denoted by omega, and they have the same amplitude of vibration. The phase of the atoms are interlocked such that the phase increases regularly from one atom to the next atom by an amount Ka. If we plug in this solution in this equation, so we are going to get this equation. minus m omega, because here on this side we have second derivative, so we need to differentiate it twice with respect to t. We will get minus m omega square a e to the power iota omega tau minus I k n a is equal to k bar a e to the power I omega t inside the bracket e to the power minus iota k a times n plus 1 plus e to the power minus iota k a times n minus 1 minus 2 e to the power minus I k a n. And by taking some common terms, e to the power I omega t will cancel out from both sides. If we take common here e to the power minus k a n, this will also cancel out. So we will have m omega square is equal to 2 k bar inside the bracket 1 minus e to the power I k a. E to the power I k will come from this term, plus e to the power minus I k a will remain from the first term, and if we take 2 common, so we will get divided by 2. So we can write it 2 k bar is equal 2 k bar times 1 minus cos k a, and if we do some mathematics, we can write it m omega square is equal to 4 k bar sine square k a by 2, or we can write the expression for omega in terms of k, because here we are having k. That's why in the beginning I write k bar, which is different from this k. It denotes the spring constant, and this k is wave vector. So omega, the relation between the dispersion relation between omega and k is given by omega is equal to 2 under root k bar divided by m mod of sine k a by 2. Or we can represent, we can represent this by omega max. Omega is equal to omega max sine k a by 2. Omega max is known as the maximum frequency, or it is known as the lattice cutoff frequency. The lattice cannot have the frequency, lattice cannot have the vibration, the frequency of vibrations greater than this. That's why it is denoted lattice cutoff frequency. इससे ज़्यादा की frequency के lattice vibrations नहीं हो सकते हैं solid में. So this is the maximum frequency. Now, if we substitute the typical value for spring constant, that is 5 into 10 to the power 3 dynes per centimeter, 1 dyne is equal to 10 to the power minus 5 Newton. For hydrogen, we take the mass of atom 2 into 10 to the power minus 24 grams, and omega comes out to be 2 into 10 to the power 3 hertz. This frequency, or if we have a chain of one-dimensional chain of hydrogen atoms, this frequency, there will be lattice waves of frequency 2 into 10 to the power 3 hertz, and this frequency lies in the infrared region. This frequency lies in the infrared region. So when the frequency is between the minimum and maximum frequency, these frequencies are allowed. These frequencies are allowed. Okay, while other frequencies are strongly attenuated, therefore the crystal behaves as a low pass mechanical filter. The lattice can allow only the lattice vibrations with frequency between 0 and omega max. If any frequency is there, has to be there, that is greater than omega max, it will not exist in the crystal, or crystal will not allow to pass the frequency which is beyond omega max. Therefore, the crystal behaves as a low pass mechanical filter. And this is how, because we have the sign term, so if we consider it in the periodic zone scheme, it will be repeated like this. It will be repeated like this. This is the dashed line is the continuum behavior when we consider the solid to be a continuous, and the two curves match at the smaller k values or when the wavelength is large. So in this region, the lattice waves are of very large wavelength in comparison to the interatomic distance. Therefore, the two curves are matching each other. But when the wavelength becomes smaller or the wave vector is higher, there is a deviation from what we expect. There is a deviation from the continuum behavior, and here the wavelength of lattice waves are of the order of interatomic spacings. Therefore, at the zone boundary, the waves would be reflected. Would be reflected in the opposite direction. That's why here we have velocity. We have this slope of omega versus k is 0 here. This means the velocity at the zone boundary is 0. It represents a standing wave. It represents a standing wave. So now we can understand this dispersion relation. So first is long wavelength limit. Long wavelength limit means smaller k wave vector. So we are considering this region only around the origin, around the zero wave vector. So the dispersion curve is periodic in nature. Periodic in nature means like we have discussed in the band theory of solids. If we consider the higher zones, they can be transferred with the help, because our lattice is periodic. Therefore, whatever parts of the EK diagram was lying in the higher zones, that can be transferred to the first Bernoulli zone. Therefore, this part of the second Bernoulli zone is analogous to this part in the first Bernoulli zone. This part of the second Bernoulli zone is analogous to this part, and this part and this part, or this part or this part, they are related with each other through a reciprocal lattice vector given by 2 pi over a. So k prime in higher Bernoulli zone is related to a k that is in the first Bernoulli zone by a reciprocal lattice vector, because our so that's why the periodicity of the lattice is reflected in the omega versus k diagram also, like it was reflected in the EK diagram when we consider the band theory. So we consider only the first Bernoulli zone, half of the first Bernoulli zone. The wave vector is between 0 and pi by a. In the long wavelength limit, long wavelength limit means wavelength is very large, so the wave vector tends to 0. Under that condition, sine ka by 2 will become k by 2, because sine x, when x is small, is equal to x. So we will have omega is equal to omega max k by 2, or omega is equal to omega max a divided by 2 into k, and it is nothing but the dispersion relation between omega and k. Omega is equal to Vs into k. It is a linear relation. That's why we have the same relation here. Here, the discreteness in this region, the discreteness of solid is not important. That's why the continuum behavior and the discrete behavior of the solid in this region, they are the same. They are the same. That's why we are getting this kind of curve here. So Vs is given by a omega max divided by 2, and Vs is also, as we have seen before, it is under root y over rho. Y is Young modulus, and rho is the mass density, m divided by volume, a cube. So, and omega max is given by here 2 under root k bar by m. So omega max is written like this, and we can calculate from here what is the value of spring constant for such springs, and it comes out to be 5 into 10 to the power 3 dynes per centimeter. And this is what we have taken here when we calculated the the frequency of lattice vibrations in the solids. So in solids, the spring constant is of the order of 5 into 10 to the power 3 times per centimeter. As k increases, as the wave vector increases or the wavelength decreases, the velocity of scholastic waves decreases as dispersion curves begin to deviate from the straight line, and at k is equal to pi by a at the right side of the first zone boundary, it saturates. Later we will define two velocities, one is phase velocity and the other one is group velocity. This we will discuss tomorrow. So with this I stop and continue tomorrow.